Yeah, so welcome also from my side. Thank you for the introduction, Rainer, and thank you especially for organizing this talk series and giving us the opportunity to really present our work to each other and hopefully also to people outside tuning into these seminar series. So in the talk so far, we've been very much focusing on regions on land, and today I'm going to take you on a journey out to the far, far ocean, and in particular the Southern Ocean, which is probably about as remote as you can get. And by the end of the talk, there's hopefully nobody left in the audience who will ask the question, but why do you bother with understanding something that's so remote and so far away from where we live and our daily lives? But before I go into this, I'd like to take the opportunity also to thank my students who are doing a lot of the heavy lifting on this project work. It's Jessica Danka, Vera Manikanda, and Ramados, and Kevin Fankuch. And again, as has been mentioned in previous talks already, they have yet to experience a real conference. And I just want to make sure that their work here is accredited and known of the contributions that they have made. The other two people I would like to acknowledge, in particular to many other project partners that I could name, but don't want to spend time here. Audran Soderwal, a scientist at the University of Lyon, who's been helping us a lot in terms of satellite products that we'll be introducing in this talk. And Isabelle McCoy, a postdoctoral fellow at the University of Miami, who again, in terms of clouds and cloud organization, has collaborated quite intensely with us on this work. So let's dive in and let's take a look at these types of clouds that we're looking at and give a first introduction to why it is that we're looking at them. So this is an image of Earth as seen from one of the satellites orbiting our planet about once a day, and it takes swaths of observations across the Earth, and so you see these individual tracks by the gaps actually in between. So this is an orbit, and these orbits are then pasted together to generate these beautifully global images. And there are two things that I would like you to notice in this picture, and I think they visually pop out quite nicely, is that a lot of this surface is covered in white clouds, and this is particularly stark and noticeable over the ocean surfaces. And that has a direct physical reason. The ocean surface is very dark and absorbs almost all incoming sunlight. So 99.3% on average of the incoming sunlight is absorbed at the ocean surface. And the albedo of the land surface is generally quite a bit higher. It ranges between 0.1 in sort of dark forested regions, as you can see here over the Amazon, to 0.4 and slightly higher in like highly bright land surfaces like the desert. So the one thing that we care about a lot in terms of clouds in the climate system is how much they reflect radiation and how they interact with the radiation, and thus what their role is for the energy balance, so the energy budget of the Earth. So generally the temperature of the Earth is set by how much energy is absorbed at the surface, and then how much energy is again in the long wave spectrum re-emitted back to space. And the role of the clouds is to reflect a lot of the incoming sunlight and thus shade Earth's surface and how generate a cooling impact. And this is particularly strong in clouds that are close to the surface, because in the long wave spectrum, they radiate thermal radiation at a very similar temperature to the underlying surface. So they have almost no long wave effect, but a very strong shortwave impact, and thus contribute to cooling our planet. And stratocumuli, which are these sort of cloud decks that span a lot of the ocean surface, are very prominent in that regard. So we have these traditional stratocumulus decks, which I'm highlighting here, one with my mouse to the west coast of South America. We also have one at the west coast of Africa, and you can see here some biomass and dust emissions and slightly brown colors on top of that white deck of clouds. And another typical deck is to the west coast of the US. And in these regions, the ocean is really covered over 60% of the time in the year by these type of clouds, who reflect on average about 30% of the incoming sunlight. And if you look down to the Southern Ocean, which here we define as south of 40 degrees south, you see this uninterrupted band, or nearly uninterrupted band, I should say, of dark ocean surface that is covered by a lot of cloud. And again, you see these sort of similar structures of these dotted white regions, or here more sort of stratiform regions of white cloud, a mixture of the two of them in this region. And you see many low pressure systems that are moving across this region. So here would be the center of one, here we have another one, and there are these wave activities on a larger synoptic scale of systems passing. And in the wake of these cold fronts, again, you see these types of dotted patterns or more stratiform patterns, which are these low-level stratocumulus clouds that we're interested in. You can quantify this, and you find that this particular region of the world is again about 30% covered by stratocumulus clouds that again have the predominant impact in terms of climate of providing shade for the surface underneath that would otherwise absorb almost all of the incoming radiation. This is another perspective of stratocumulus, this time looking from the bottom up, and it really quite nicely highlights the sort of key figures or features of these types of clouds. So they're very shallow in vertical, they only extend a couple of 100 meters, whereas convective clouds, and tropical storms extend over several kilometers. They're very shallow in extent and form near the surface, and as this image visualizes quite nicely, they block out a lot of the incoming sunlight, and in the whole regions where we have no cloud in between the gaps, sunlight is coming through and hitting the surface. As opposed to the stratocumulus decks in the subtropics, the Southern Ocean is a lot colder since we're going out further to the poles. And that means that these type of clouds are a little bit more complicated than their subtropical counterparts, because they don't only exist of cloud water, so water vapor that is condensed to form cloud droplets, but contain a mixture of cloud ice and cloud water within these clouds. And the thing to know is that inside mixed phase clouds, the radiative effect, which is the one that we care about the most, is still constrained by their liquid water part. Even though these guys form ice, the ice crystals nucleate somewhere near the cloud top and then grow as they sediment down out of the cloud. They have a very weak interaction with the shortwave radiation, because for the same amount of water, they tend to be considerably larger, and there's very few of them. So they don't generate a lot of surface to scatter sunlight and reflect it back out to space. So in terms of the climate impact of these clouds, ice can be viewed as a sink on water, because due to the thermodynamics of this system, when your temperature is colder than freezing, all ice crystals will always grow at the expense of liquid water. It's energetically favorably to be in the ice state as opposed to the liquid state at temperatures below 0 degrees. So as ice nucleates, it very rapidly and efficiently draws the liquid onto it, and then as the ice crystals fall out of the cloud, they take that water that's come from the liquid phase to the ice phase with them. So they generally reduce the liquid water content within these clouds as they form ice. And the other thing that you see in this image is that this is a sort of average or typical precipitation rate. It could be a bit more than that at the surface. But in terms of moisture flux to the surface, they really play a very minor role compared to fronts or any other storm systems. Most of the precipitation that leaves cloud base actually sublimates or evaporates, depending on which phase it is, in below cloud base. And that drives an important feedback on the dynamics of these clouds, because as they evaporate and sublimate, they cool the subcloud environment, which then organizers and favors and other types of updraft regions to occur for the stratocumulus cloud to stay alive. The other thing that you should know about mixed-phase clouds is that the ice at the temperatures that we find them at, so yes, it's cold in the Southern Ocean, but we're still very close to the surface, and temperature decreases in the atmosphere as you go up. So we're still at relatively warm temperatures of -3 or -15 down to -20 degrees Celsius. So the only pathway for ice to form inside these temperatures and for the given aerosol species that we know are around is through the liquid phase, or something that's we call immersion freezing. So at some temperatures, there'll be some aerosol inside the cloud drop that activates, and then the cloud drop glaciates and we form an ice crystal. So if the ice growth mechanism is too active inside these clouds, then all the water will condense onto this, freeze onto this ice crystal, and the cloud dies. Once the cloud's glaciated, it's really hard to recondense water from the vapor phase, because the general thermodynamic structure of the boundary layer is very dependent on the effects that the cloud water has with the interaction. So the ice is a sink on the water content, and if the sink is becoming too effective, it kills the cloud. So it's a very complex thermodynamic and microphysical system that we're trying to simulate here and understand. And the thing to keep in mind from the slide really is that it's in the end the liquid that determines how much incoming sunlight is scattered. And this is the one big slide that I want to spend some time on to tell you why it is that we think about this or worry about this at all. This is a study published by colleagues led by Mark Selinka, looking at the cloud feedback. So as the planet warms, it literally burns away low-level cloud and makes low-level clouds less reflective, which accelerates the amount of warming that the planet experiences. And that's what we summarize as cloud feedback, and that's particularly what governs the low cloud feedback. And you can quantify this in additional watts of meter squared, so the energy flux into a particular area per warming of Kelvin. So this is the amount of extra warming that's generated as the surface temperature of the planet warms, and this time here it's quantified in terms of Kelvin. And in the IPCC reports, these estimates provided in regular intervals, and they're very heavily based on what we call CMIP intercomparison. So these are climate model intercomparison studies where a whole range of models across institutes and across the world are run for a set of experiments, and then the climate sensitivity of these models is compared, or the cloud feedback of these models is compared, and the overall global estimate is assessed. And what you see here in blue is a past generation CMAP configuration for the earlier IPCC report, and in orange you see the new generation of climate models. And I want to particularly focus you on the right-hand side of this figure, looking at the shortwave low cloud feedback. And in black, you see the mean estimate, and the spread is shown in the clear colored circles. And you see a clear upward shift here. So the newer generation climate models predict a stronger low cloud feedback compared to the past generation climate models. And that is entirely attributable to what's happening in the extratropics and what's happening in the Southern Ocean. In CMIP5, many of the mixed phase clouds that were simulated, which again occur around 30% of the time, were too heavily glaciated and didn't reflect enough radiation in the pre-industrial climate state. So their feedback as you transition to a warmer climate was underestimated. Models that have fixed this bias in the previous generation model generation now simulate a considerably stronger cloud feedback in the Southern Ocean. So even though these clouds are in only one particular region of the world, the effects, the radiative effects that they generate are enough to matter globally and to impact climate sensitivity estimates. And as I tried to convey with the earlier slide, representing this cloud system in models is rather challenging, and that's why we spend time in our project on this, but many other groups around the world also focus on this problem to understand these clouds first and foremost, and then represent them in models across scales. So the composition in terms of water and ice impacts the reflectivity of these types of clouds, or the albedo. And the other thing that we know is that the organizational state of them also does. So stratocumulus tend to organize into different types of patterns. So we either have stratus cloud that is completely diffuse. You can think of it as an optically thicker fog, really, that forms above Earth's surface. And as these clouds are starting to retain more water and become more dynamic, they organize into different patterns. And here we distinguish between open mesoscale convection, so that's what MCC stands for, or closed mesoscale convection. And these structures are very much like honeycombs that persist over hundreds of kilometers within these decks. And the open MCC is characterized by a lot of clouds along the cell walls, and then very little or optically thin cloud within the cell center. Or we have these closed cell clouds, which are the inverse, where you have a lot of cloud in the cell and a ring of clear sky around the edge. And what Isabelle McCoy, the collaborator of this project, showed in previous work is that the reflectiveness of these clouds is impacted by how they organize. Now, in this images here, which show the organization, you go, well, of course, there's a lot less cloud coverage, right, in this image than that, so that's maybe not surprising, but she stratifies for that. So even if the regime is covered, like 40% of the area is covered by cloud, the open cell regime is still going to be less reflective than closed cells. And that has to do a lot of the dynamics of these types of clouds. And this process, or this characteristic, was isolated in this study. So that opens the question into, well, if in a changing climate we have a different occurrence of these types of states, let's say we tend to favor open cell as opposed to closed cell MCC, then this is then also a feedback to be considered in terms of the albedo or cloud feedback in this particular region. And the particular focus of this project is to explore how these two are linked. So in the current state, we still have a lot of mixed phase clouds where we have ice as a sink on the liquid water, making these clouds less reflective. And we know that they tend to organize into these different regimes. As we go into a warmer climate, we will know that at some point it will be too warm for these clouds to generate ice in the future. So that sink on the liquid water content will disappear. That's why these, for a short time, will become more reflective before other effects take over. And that's what we know as the cloud phase feedback. And it could also be plausible or conceivable that the organizational state of these stratocumulus regimes is also impacted by this change in phase or by other changes of external drivers. And that's what we explored here. And here I show you results from two studies that have sort of motivated this idea. One of them was led by Geza Iron, the PhD student who I co-supervised at ETH. And she was doing this for some simulations of Arctic open cell stratocumulus. And she was looking at the cell diameter of these of the cells that she was simulating inside the stratocumulus deck. So we're looking at the size of the honeycomb itself. And the line that I want to focus you on is the blue line here that shows that after some time, we tend to grow larger cells in simulation that generate a lot of ice production. And then this translates into a noticeable radiative effect, because as they increase in cell size, you detrain less cloud within the cell centers. It changes the reflectiveness inside the cell and actually makes it less transmissible to radiation. So that's the one set of indication in these proof of concept studies that organization and phase may have a combined impact on reflectivity. Another study was recently published by looking in the northern hemisphere at cold air outbreaks in the North Atlantic. And as you have these cold air masses pushing down from the poles equatorward, you have these typical transitions from different organizational regimes and stratocumulus, going from roll clouds to closed cell to open cell clouds. And the previous study in 2017 had shown or had argued that supposed to the subtropics, a lot of this transition from one regime to the other is driven by precipitation. And the new results from Possner et al. Now suggest that this transition from the closed cell to the open cell state is actually accelerated by ice production within these clouds. It takes longer to generate the same amount of precipitation through the liquid phase. So to make a cloud rain, it takes a little while to have all these little cloud droplets collide and form larger rain droplets. Whereas if you have one ice crystal that freezes, it grows quite rapidly and falls out of the cloud and sublimates in the subcloud layer, changing the thermodynamic profile underneath the clouds. And that sort of presets or facilitates a quicker transition from one regime to the other. So to have a look at whether or not this occurs frequently, or if we can detect signals of that in a statistical sense, we looked at this in the Southern Ocean using remote sensing observations from the A-Train. So the A-Train is a satellite constellation that's been orbiting our planet for many years. The satellite images that you've seen so far were generated from MODIS, which sits here on the Aqua satellite, and that looks at the backscatter of radiation that comes off our planet. And we can generate these visual images that you just see, or we can infer other diagnostics from it in terms of where does the cloud top height sit, what is the composition. There are attempts at phase, although they are less reliable from MODIS for various reasons. And behind Aqua sits Calypso and CloudSat. These are different approaches. So they actually send out an active signal down to Earth, and that's then reflected backwards, and that's what we analyze. So they can provide a vertical profile of these clouds, and a combined assessment between Calypso and CloudSat, which do this at different frequencies, allows us to distinguish what the vertical phase distribution is within these types of clouds. So Jessica has been looking at this in the years 2007 and 2010 and has compiled a database and looked at the sort of the statistical relationships of these clouds. And this is to give you an example of what this looks like, what she's done here. So you see a cross-section of the cloud, and you see the height here on the y-axis, just to orientate everybody, and the latitude here on the x-axis. So we're following one of these swaths of the CloudSat and the Calypso satellite, taking a profile of the clouds and the atmosphere. And everything that's here in contours is a cloud that's categorized vertically by its phase. So green stands for mixed phase, so with both LiDAR and radar detect both liquid and ice at the same place. Orange is a pure liquid region, and then blue is just cloud ice. The cross-off region here is a region where we are unable really to provide an estimate of what phase of cloud it is. That's because the LiDAR usually is saturated at this stage, and the radar is very much impacted by what's reflected back off the surface. So we can only really provide these types of estimates above 750 meters. Below then we're impacted by what's called a surface clutter, and we can't trust the retrieval. And as you can see here, then we can categorize these clouds as a pure liquid cloud. This would be mixed phase clouds, again, followed by pure liquid mixed phase, etc. And she's combined this data set with a data set by Isabelle McCoy that's classified these cloud scenes using the MODIS images as open and closed cell mesoscale convection. So in the end, we have sort of the summarized product where we categorize, give a vertically integrated assessment. So yes, this column is classified as mixed, so which is shown down here in green, and then open and closed circles indicate where we said it's open or closed cellular convection. And then with this data set, she's looked at various correlations of different quantities and relationships in these clouds to understand whether or not we see any impact or interrelation between phase and radiative properties through organization. And this is what I want to show here is one of our key results. If we look at cloud optical depth, so that's related to the extinction of shortwave due to clouds, we see here in yellow the liquid distributions for different seasons, and in green the mixed distribution, so for mixed clouds for different seasons, and then here for open cell, so that's the cloudy cell wall with very little cloud in between, the closed cells, vice versa, we have the cloud in the center and the clear sky breathing across it, and then for all low-level clouds, including other types of organized stratocumulus, but also shallow cumuli, etc., etc. And what you see here is this noticeable shift towards higher optical depth clouds between liquid and mixed phase clouds. And this is particularly stark in open cell, where we see a very strong cutoff around an optical depth of 10-15, with very few liquid clouds that are optically thicker. All of the clouds that are optically thicker also generate ice. And that's something that's not immensely impacted by cloud phase. I mean, the overall shape is the same for open and closed and all low-level clouds. But what you do see is if you focus in what's happening between an optical depth of 10 and 25, that in particular in closed cell states, we have a penetration of the liquid phase into higher optical depths. So whereas all of these optical depths around 20 and 15, and these are really then practically opaque clouds, while all of these guys will already be generating ice in the open cell state, we still see them in the liquid state at these cloud optical depths. But otherwise, in terms of the general statistics, there's been very little seen between open and closed cells. This is also visible when we try to assess and characterize the freezing behavior of these type of clouds. Again, if we look at the green dots, those are the mixed phase clouds, the orange are the liquid phase clouds, and we look at open cells, closed cells, and all low-level cloud statistics. In the first row, we do this for austral winter, and in the bottom row, we do this for austral summer. If we look in the top row for now, we again see very little difference between what the mixed phase and the liquid phase clouds do for the different MCC regimes, and in fact, with regard to the general low-level cloud climatology. We do see stark differences across seasons though, so austral winter tends to show generally more mixed phase clouds than austral summer, and this is the case for all regimes. And we see this growing arc of increased mixed phase cloud occurrence for temperatures colder than -12, which we understand quite well through different freezing mechanisms that are happening inside these clouds. The only thing that we do see in terms of the relation between organization and freezing behavior is what's happening around -5, -6 degrees Celsius. So you see this upward increase of mixed fraction again, which is slowly coming down as we go to warmer temperatures, you expect, but you sort of see a revival of mixed phase clouds around this temperature peak. And that's something that's very much related to Hallet-Mossop, which is a Rhine splintering process. So in this temperature regimes, ice crystals fragment due to collision and shear processes. Larger ice crystals fragment into many small ones, and then the freezing process is proportional to the surface, and many small crystals generate more surface, so they actually tend to grow overall quicker and generate a higher ice water content within these clouds. And that's something that we see in open MCC, but we don't really see to the same extent in closed MCC clouds. But even so, and having said that, it's very clear that the phase is not predominantly constrained or related to mesoscale organization, but it's other drivers that are controlling how much ice forms inside these clouds. And here I show you the same figure where we now don't look at it in terms of cloud top temperature, but we're looking at it the same relationships in terms of cloud top height. And here you see that for clouds that are at a higher altitude with their cloud top, they tend to contain more ice. So the ice fraction or the mixed phase fraction goes up as we go to deeper cloud depths. And the same is seen for austral summer, but even more pronounced. And this increase in pronouncedness between the two seasons makes sense. And austral winter, it's generally colder as we are in winter. So you're reaching the temperatures that are efficient at ice nucleation already at lower altitudes. Whereas in summer, you need to go higher up to reach the same cold temperatures. So it makes sense that this relationship is more starkly pronounced in summer than in winter. And again, it's something that shows across the different regimes for open, closed, as well as all level clouds. And it just shows that cloud top temperature is not a very good assessment for like the trigger onset of mixed phase clouds, as many other ice growth processes all co-vary with temperature. It's hard to isolate the occurrence of the onset of ice with changes in cloud top temperature, but they very much respond to the amount of mixing that has been generated inside these clouds. So the depth of these clouds is governed by how much the air is descending down and how much the turbulent mixing is pushing against that, and the cloud not being pushed down all the way to the surface. So that's why we can infer from this relationship of looking at cloud top height that mixing seems to be playing a role, and that's what we identify from the satellite-based point of view, and it's been seen also in field studies, and that seems to be showing a quite consistent picture. The other thing that Jessica has found that surface-driven mixing doesn't seem to explain this relationship. So it's still cloud scale processes that seem to generate the mixing as relevant here. So the findings of this study seem to show that mesoscale organization does not seem to provide an additional constraint on cloud phase. There's no evidence for preconditioning to happen. If this is a dominant process, then we would expect to see shifts in the occurrence of mixed phase to liquid clouds between open and closed cell states, because if closed cells are generally less stable in the mixed phase and transition earlier a lot of the time, you would think that that shows up in the climatological statistics. It doesn't mean that it's a process that can't occur. It may well occur, but it doesn't seem to be the dominant constraint or a dominant indicative of a dominant relationship between cloud organization and cloud phase. And that sounds like maybe a bad thing. We kind of set out hypotheses, right? We want to be right and show that they're true. But in the end, I think it's a good thing in terms of climate model assessments, because mesoscale organization is not something they capture. So that's these studies, or this study from Jessica, indicates that that's not necessarily a bad thing in this particular problem because the two aren't related. There are still secondary effects that we're exploring. So the study I showed earlier from Ivan et al. Showed this inference from cell size to reflectivity, so larger cells being less interactive with the radiation. And that's something that Jessica is still working on right now, and we're looking forward to the results of that. Now, while the remote sensing has been really great in looking at the statistics of these kind of clouds, we are hitting limits with this as well, because when we look at the full dynamics of the system in terms of, what are the cloud scale mixing processes and things like this, is not something we can assess and we have a good set of data on. So we try to combine this with numerical models that give us this information on mixing, on three-dimensional variability, not just in clouds, but also in dynamical properties. And the model that we use for this is the icosahedral non-hydrostatic, or in short, ICAN model. It's a new climate/weather forecast model on the market. It's been co-developed by the German Weather Service and the Max Planck Institute for Meteorology in Hamburg. And the great feature about this model is that it has a rather unusual grid. I think we're all still of the generation that might have had a globe in their kids' room, right? And they tend to show a very different type of grid. There's traditional longitude and latitude grid. And that has a severe problem, and that's where the axis goes through your globe. It has a singularity at the poles where the mesh breaks down. And ICAN doesn't have this problem anymore. If you go to the triangular mesh, or like more of football, pentagonal mesh, you can circumvent this, and then ICAN use the choice of triangles, so you don't have any issues with singularity. And what you can also do in this model is you can nest it down to higher resolutions over a region of your interest, and in our case, that is the Southern Ocean. This is a summary of global simulations across many different models that were performed during the Diamond Initiative. So there's this general push in climate models to circumvent the cloud problem that we know exists in core scale models and go to higher resolution models that doesn't require a subset of the parameterizations that are still needed in core scale models. The catch of that is that it's computationally very expensive to run, while institutions across the country and internationally are able to run this. Individual research groups are not able to do so, and I think the computational costs are summarized here in this table, and it just blows up in terms of computational resources as you go down to global simulations that are performed at a 2.5–5 kilometer scale. And I highlighted the red 2 here in particular because the type of computing resources that is required for one of those simulations is, I think, it ranges between a 7th and the 17th of the entire annual computational budget of the group that we have. So it's a great data set for us to look at, and it's worth looking at these simulations just because of the amount of resources that would be required to regenerate what they've already known and provided. And this is a figure of the simulations published by Stevens et al. And he likes to show this figure and ask, well, which one is the observation? So one of these globes is the satellite observation, and the rest of them are the climate model simulations performed at a 2.5 kilometer scale. And what is really nice about this now is that it becomes really hard to distinguish between the satellite retrieval and the simulation. And that's partly because these models are so good, they still have biases that are visible, but generally the overall features are now captured, and the overall physics is, or a large fraction, I should say, of the overall physics is captured. And also in terms of scale, the modeling approach and the satellite approach are converging onto the same resolution. So satellite products are available about 1 kilometer, resolution, and that's now where also these global simulations are headed, and different experiments can be run. And we use this data set to look at what's happening in the Southern Ocean. And what I show you here now is just a latitudinal cross section going from -40° south towards the South Pole, once for the mixed fraction, so the mixed occurrence of mixed phase clouds on the left-hand side and the occurrence of liquid clouds on the right-hand side. And in black is the observation as seen by the data product. So again, the Calypso and CloudSat were integrated, as you've seen earlier for Jessica's work. And if you look at the mixed phase fraction in this plot, it doesn't actually look so bad, right? You see this shape that is roughly captured. There might be an overestimation here, but it generally seems to follow the mean from the satellite. And it doesn't seem to suggest that there's a stark dependence on model resolution here. So the different lines correspond to the same run going starting at an 80-kilometer mesh size, going down to a 2.5-kilometer mesh size. So, and the mixed phase fraction as well as the liquid phase fraction for most of it don't seem to depend strongly on resolution. For the liquid fraction, you see dependence as you go equatorward. So higher the underestimation in liquid clouds is sort of helped by resolution in this part of the world. But as you go further poleward, there are just no liquid clouds simulated in ICAN of this particular configuration, whereas the observations are telling us there should still be a fraction of 20% happening. Part of the behavior that we see here is due to the fact that we see like no clouds or glaciated clouds in this region of the world, which shows this drop off in mixed phase fraction. If we normalize this for all clouds that contain liquid, how many of them also contain ice, then this is what the observation is showing us. So across the latitudes, we see this sort of mountain structure where we have an increase as we go poleward and the temperature decreases, and then during the August month, a stark decrease as we go further poleward. And that decrease is related to the ice sheet that's penetrating equatorwards in Austral winter. And we see the inverse correspondingly in the liquid phase, where we see a bathtub shape, where the liquid fraction decreases as we go poleward and then increases again, or recovers towards the pole, where the ice sheet is limiting ice production inside these clouds. And this behavior is completely missed by all ICAN simulations across all model resolutions. And the reason we care about this, again, is linked back to the radiation. So here we look at the bias and radiation of these ICAN simulations, and you see the net shortwave flux is observed from space on the top here, and you see the bias for one of the ICAN simulations, and this shows you a distribution of where these mixed phase clouds are sitting. And you see a lot of red here, which means too much shortwave radiation is making it down to the surface, and that's exactly the regions where we have these mixed phase clouds. As you go down in model resolution, this is the bias average now over the entire region. It reduces, but that's due to a combination of factors. Yes, it helps with the bias inside of these mixed phase clouds, but it's also due to a compensation of errors. So regions where you see blue here, so the clouds are too reflected, correspond to regions of pure liquid clouds. And as you go down in resolution, the pure liquid clouds become more reflective, which compensates for part of this red bias. So although the table here would suggest that the problem gets better with resolution, it's actually in large part due to a combination of competing biases. So it doesn't go away, even if you run your climate model in the end at a 2.5-kilometer resolution, this mixed phase cloud problem in ICAN still persists. And a lot of this is due to the microphysics representation within these clouds, and that's something we're assessing within a field campaign-based approach of simulation, because these global simulations are so expensive at the kilometer scale or even higher resolution. So we go back to running case studies where we have observations of this. And ground-based observations, like were the ones that were taken during Capricorn, one of those ships heading poleward from New Zealand and continuously measuring the atmosphere, is that we have a much higher spatial and temporal resolution of these observations as from space. And this is now work that's led by Veronique Kanden, Ramados in my group, and he's coupled the ICAN model to a radar simulator. So we pretend that ICAN is the real atmosphere, and we pretend we have a radar in it and see what it sees, and compares the observation to the retrieval mouse. On the top here, we see the Capricorn retrieval, and on the bottom, we see one of the ICAN simulations of the same track. And what we see is that I can actually capture the intermittency of these clouds. So we have this sort of barcode structure in reality, which is also captured by ICAN, but there's still some biases. So total ground-based precipitation is overestimated, and these intense precipitation peaks that are in the core of the updraft within the observation are also missed by the model. And if we look at the distribution of radar frequencies, which generally larger frequencies are associated with stronger or larger precipitation, we see this like growing arc of large precipitation in both the observation and the simulations, but within the clouds, where we have this bridge structure here at intermediate reflectivities, which are indicative of smaller amounts of hydrometers that are precipitating, they are completely missing within the cloud and are only showing up near the surface. So there are biases within ICAN, how it's forming and where it's maintaining precipitation within the cloud or near the surface, that we can analyze with this type of modeling framework. And the one thing that other people have shown in several studies, and something that we also see here, if you care about the amount of ice that's generated inside these clouds, it's very sensitive to the microphysical setup that you choose. So there's no need to understand all of these individual acronyms, although some of you might wish to. What I do want you to see is that the ice ratio within these clouds ranges from 2% to 14% for the same simulation with just a different setup in the cloud microphysics. And we can constrain what the real setup or the best setup should be and explore some of these sensitivities with an ICAN to get to a realistic representation of these type of clouds. So to summarize on a sort of higher level, what I would like you to take away from this is that these types of clouds are important as they cover vast regions of the ocean surfaces and provide shade. I think I've shown you that their physics is complex, and their misrepresentation really skews our estimates of global climate sensitivities. And a lot of the processes that we learn in the Southern Ocean are also applicable to clouds in other regions of the world, Northern Hemisphere, exotropics, as well as the poles. And that is really a problem that we need to tackle, because even as climate models are approaching higher resolution, it's part of a physics that will still need to be represented, as resolution alone is not helping to solve this problem. And with that, I'll take any questions if there are. Thank you.
Okay, thank you very much for this very interesting talk. If there are questions, then please put them in the chat or in the question and answer tool. While we're waiting for people to type, I'll ask my first question. So you explained nicely how the clouds disappear, so to say, because snow might form, right? But how do they then form in that region? Is it that do they form spontaneously, or is it clouds that grow and then separate, or what? Yeah.
Yeah, it's a bit of a chicken and egg problem, because they do tend to reinforce the types of structures that are required for them to form. I mean, initially it's just condensation of water vapor in a very moist region, where it's cold enough or the air is super saturated and then it can't retain all of the water in the vapor phase any longer. And for them to really form as stratocumulus, you need to have a strong inversion near cloud top to trap the moisture really near the surface to generate these like vast cloud fractions within these decks. So, you know, if you go into the mountains, you tend to have these foggy layers with clear sky conditions above, and it's these type of inversions that are also needed for stratocumulus. And that's where the sufficient supersaturation is generated for cloud water to condense.
Mm-hmm.
And
okay.
yeah, and once it condenses, it interacts with the radiation in such a way that it actually strengthens the inversion and keeps it alive. So what was first inversion or cloud is not always a clear-cut problem.
Mm-hmm. Okay, thank you very much. So can
I ask a question, Qin Wang?
Yes, yeah.
You can hear me, right? Yeah, it's a quick question. It's very interesting you show this, the PDF of optical thickness around, you know, against a fraction, you know, liquid and ice. You know, one you did that in the seasonal average sense. You know, one thing we don't know is whether it's the frequency or the periodicity of these interesting structure form. So have you done any sub-seasonal analysis to see the PDF, similar PDF would be appear, or you know, how is a sub-seasonal PDF would showing any similarity or actual difference from the seasonal mean? That'd be quite interesting, right? So because we don't know, another factor of this question is how much IMP available. So that's always a mystery, but at least from the remote sensing side, this would be a quite an interesting lead. Just wondering. Yeah.
So we've not looked at sub-seasonal statistics of this. I think is what I think you're getting at are these like transitions, right? When do open cells form and how do closed cells form? Yeah. And I mean, we do know that they tend to sit in these cold out air break structures within the Southern Ocean. So very much like that image that I showed from the Northern Hemisphere Atlantic picture. And there we have this pretty preset evolution of conditions from closed cell to open cells. That's generally the dominant pathway in terms of the dynamics of these types of clouds. There are backward transitions that can be generated through concentrations in CCN conditions, but I don't think that's the dominant pathway especially in the Southern Ocean. But to do this properly, you need to change your approach. So you need to really follow the MS and do this Lagrangian in a Lagrangian sense. And I know people that are doing this. I'm aware of works going on at the University of Washington, also in the same region, but we're not doing this here.
Okay.
But it's an interesting part of the puzzle, and I think that would be nice to see in terms of the transitions. But yeah, in the end, if you think about it in a climate sense, you need to see shifts in the statistics of it to really matter, and that's the part of the puzzle that we explored here.
Oh, by the way, a quick comment that you say this is a SIMP 6 model might be newer model. Most of them might not be newer model in the climate sensitivity, in my understanding, because because they all use a prescribed liquid water fraction. So that's you're kind of adding a restriction rather than changing the physics itself, right?
I'm not.
No.
Some of the I think Hatchin free they actually changed something in their physical setup by generating enough turbulence to keep the liquid phase alive by recondensing enough water. other models might have done this in a different way yet. I don't know the details there, I'm afraid. But yeah, it's just an example to show, you know.
I know.
Okay.
Making fun of the models.
Yeah.
Okay, we have a question by Camille who raised her hand.
Yeah, so I'm going to ask a very naive question. This is not my field at all, at all, at all. But what you were showing, seem to be showing, is as you get warmer temperatures, you get less ice formation, which makes sense, right? But then that would mean that you would have more liquid cloud, right? A more stable cloud, because the ice, you said the ice causes the cloud to disappear. So wouldn't that give you actually a negative feedback to the warming trends rather than a positive feedback? So wouldn't warmer air then lead to more cloud, which would lead to more reflectance?
That's yes, yeah, it's a very good question, and that's where different types of cloud feedbacks intercompose on top of each other. So one of them is this what we describe as cloud phase feedback, this pure no ice, and then it's all in the liquid, and thus the same amount of cloud is more reflective. But cloud amount changes, so the cloud fraction that you have changes by other drivers again. And as you warm the climate, you change the stability of these type of clouds, and it's literally you burn them off, and that's still happening. But this cloud phase feedback goes into the other direction.
So that's why the CMIP6 was giving a stronger warming than the CMIP5.
Yes, because the cooling effect was overestimated, and then that overestimation has been taken away, which increased the overall cloud feedback in a positive sense.
Okay, great. Thank you.
Okay, I think that discussion also answers the question from Alessandro, who asked, can you comment on what the modeling shows will happen to low-level clouds as temperature increase and how the feedback will operate? But Alessandro, if you have a further question to that, you can open your mic, or I don't know if Anna wants to.
No, that's great. Thank you very much. No, you did a good job already of addressing my question. Thank you, Anna. Excellent.
Okay, perfect. Then we have a question from Marion Carrier. Do you use physical-chemical characteristics to describe or model a cloud? If yes, how do you measure those properties?
So physical or chemical, you mean? Yeah.
Physical-chemical characteristics, yeah.
Of how I model these clouds. So we use different setups that have a varied complexity here. So while a lot of the amount of water that you have is primarily constrained by the thermodynamics, so how much moisture and what the temperature is in the air, that can be modulated by the amount of aerosol that you have. So in terms of CCN activation, so for the droplets, CCN concentrations can change, and for the triggering of freezing, INP concentration is actually a limiting factor in these type of clouds. And most of the standard CMIP models, they don't have any active intercoupled representation of this. And we have a intermediate complexity approach where we don't have the full chemistry of it, but we have the typical aerosol size distributions, and then can really compute what fraction of these aerosols will activate for a given set of supersaturation at this particular location, and the same goes for the immersion freezing. I'll be happy to chat in more detail about this, but I think it's probably not interesting to the broader audience, so we can talk more if you want more detail on that, what we do.
Thank you. Thank you so much.
Perfect. That's of course also the reason why we have the seminar, so that we get people in contact and that you can discuss also outside of this. Maybe I have a final question. I think it's amazing work that you're doing, and I wonder, like, all the satellite data analysis, do you use image recognition to characterize the different cloud types, or what do you do there?
So at the moment we use a data set that's already been generated by Isabelle McCoy, and what they did is they did Fourier transforms of these features and then through them characterize them. But we also have ongoing work by Christoph, who I've not shown here, who is doing this from using neural network approaches to classify these images. There's already a couple of groups that have done this type of stuff, but that's where we're going to try and head for, to really link this from the modeling and the remote sensing perspective to classify, look at the radiative properties and move on from there. So it's ongoing.